Hey guys, Greaves here. Um, so this is going to be our last video together. I know that many of you are going to be upset about that. If you're feeling bad, plus pause, go get some tissues, maybe some Kleenex or something like that. Get yourself all ready to go, and then come back. Okay. All right, we're back. All right. Anyway, all right. So we have the last thing that we need to look at, right, in physics, okay? And it's kind of the world of the strange, right? And kind of odd, right? But I'm just going to go through it, and I'm just going to give you, a general view of things, of how we think things are. Okay, so on your reference table, right at the bottom on page 3, you're going to have two little tables. Okay, let's take a look at this one right here first, okay? So this is what we think matter is made of. What do I mean by matter? Me, you, the air that we breathe, right? All the elements on the periodic table. So let's just take a look at this chart right here and let's follow along. So this is matter. Like I said, every element on periodic table is considered matter. Really, anything that has mass, right, is considered to be matter, a particle. Believe it or not, we had talked about light. Light actually is a particle, but it's not matter. Why is that? Because actually light has no mass. It's really this strange particle, right, which has no mass at all, right? And if we were in class, we'd get into it a little bit more, but not gonna, right here at this forum, right? Too much to discuss. Okay. So what does matter? What is matter consist of? What do we think? Well, we have two separate particles, okay? Or two different classifications of particles. Number one, we have something called a hadron. And by the way, I didn't make up the names. Don't yell at me, right? And then we have things called leptons, okay? So what's the difference between a hadron and a lepton? All right, well, here's how it goes. Hadrons, and I'm going to say the term, are relatively large particles. Hadrons are relatively large particles that has other things, I use that in quotes, inside. So hadrons, relatively large, are made up of other things. Leptons, all right, well, what's a lepton? Well, a lepton is a particle that has nothing inside. And by the way, you might say, well, how do you know that, Greaves? Well, the answer is these fancy things called particle accelerators. We take hadrons, spin them in a circle very, very fast, right? And we smash them into one another, right? When we do that, we always see that 3 or 2, I'm not going to get into it right now in a second, particles pop out. So if I could smash hadrons together, right, we get other particles come out. If I take leptons and smash them together, nothing pops out. All right, so what's an example of a hadron and what's an example of a lepton? Well, an example of a hadron is a proton or a neutron, right? We'll talk about that in a moment. What is a lepton? Well, if I take a look at this chart over here, one specific example of a lepton is the electron, right? An electron we think is fundamental, nothing else inside. Okay, so matter, hadrons, leptons stand on their own, hadrons do not. What do I mean by that? If I crack open a hadron, I have two other now particles, baryons and mesons. Remember, hadrons are relatively large particles with things inside. There are two classifications of baryons. Two classifications of hadrons. One is a baryon. All right, well, what's inside a baryon? Well, lo and behold, if I take two hadrons, which are baryons, right? Two baryons, which are hadrons, I should say, and smash them together, I always get 3 quarks, right? Now, hopefully, or maybe you've heard of the term quark before. This is what we think, right, is a fundamental building block of matter, right? Just like the lepton, right? The electron is fundamental, right? It stands on its own, right? If I take 3 quarks and kind of arrange them together, I get a baryon. All right, so that's one type, baryon, 3 particles. What about a meson? All right, what's a meson? Well, oddly enough, it has 2 quarks inside. Now, I'm going to say something here and it's going to be a little bit weird. A meson consists of a quark and an antiquark. Now, yes, okay, there is something which we call antimatter. It is not science fiction. It truly does exist. One of the major questions of the universe is, why isn't there a lot of it, right? Well, the answer is we don't really know. Where do we produce antimatter, right? Inside particle accelerators again, right? So, now, matter. Hadrons, leptons. Stuff inside, no stuff inside. Baryons, mesons. 3 particles, 2 particles. And I'm going to talk about antimatter in a moment, right? But 2 particles, which happen to be a quark and an antiquark pair, okay? So now, let's take a look over here. So now, what we have, as far as we know now, these are all the fundamental particles that exist in the universe, right? And depending on how I kind of put them together, right, I get different particles, right? So I'm not going to get too crazy with things, right? We're just going to take the basics, okay? So let me just take a look at this chart again, just to let you know, right? How do I like to look at this chart? Actually, it's 2 charts, but I like to take a look at it at one. I want you to look at it as a chart that has 3 columns, see it? And 4 rows, right? 3 columns, 4 rows. All right, why 3 columns? Well, I'm not really sure, right? I don't think many people are, but I'm going to tell you something. Column number 1. These quarks and this lepton are very stable, right? What happens when I hop over to column 2? Well, believe it or not, what happens is this particle now, these columns, right? These particles have a little bit different mass, but unfortunately, which makes them a little bit unstable. As I hop over here, now these particles are even more unstable. So what does that mean? Well, if we produce them, once again, particle accelerator, they kind of hang around for a brief moment of time and then degrade into something else, okay? Now, let's look at how I can put these things together to make particles which we're familiar with. There are other particles. I'm not going to get into it here, okay? So how do I arrange matter, okay? So let's take a look. All right, so I'm going to draw it like this. I'm going to leave this here, right? I'm just going to look at this guy right here. Hopefully you guys can see that. All right, so let's take a look. What are the rules of arranging matter? So we have some rules. 1, right? Particles must have an integer number of charge, right? So particles must have an integer number of charge. So that's number 1. Number 2. And yes, this is like the science fiction movies. Matter and antimatter cannot exist together, right? What happens is if I get a particle and an antiparticle, they will annihilate each other like yesterday, right? Proton and antiproton. So what that means is, yes, there is an up quark. And by the way, the quarks, like I said, there's a lot I have to kind of do here, and difficult to do it on a little YouTube video, right? So let's take a look at this guy here. What's the name of this quark? Well, we call it the up quark. Don't ask me why, I didn't name it. Its symbol is a U, and it has a charge of 2/3 E. It's weird, right? 2/3 E. What's this guy? Down, D, minus 1/3 E, etc. Charm, C, and you'll see the charges are there, right? So how do I put things together? Well, rules must have integer number of charge, right? And matter and antimatter can't exist together. So what that means is, right, so if I have an up quark, right, there's up, right, 2/3 E, there is something called an anti-up. I'm going to write it like this. That's U, and it's a bar over it. And what's the difference? It has a minus 2/3 charge. We're not going to get too crazy with it, right? Just to let you know that this chart is actually another duplicate chart. Everything's exactly the same. Anti-up, minus 2/3. Anti-charge, minus 2/3. Anti-down, plus 2/3, plus 1/3. Just opposite charge. Okay? So let's just take a look at a couple of particles. All right. Hopefully this will kind of gonna make sense now. So let's make a particle that you and I are or should be familiar with. Proton. By the way, a proton, right, is a baryon. I'm telling you now, it's a baryon. It has 3 other particles inside, 3 quarks, right? So I'm just going to draw it like this. Here's the proton. It consists of 3 other particles. Okay, so how can I arrange, right, quarks to give me a proton? All right, so what's the charge on a proton? Well, we know that it is 1e, positive 1e. All right, so I have to ask a question. Is a proton a stable particle? Unstable? Well, hopefully it's stable. It's been around for more than a couple of billion years, maybe 14 billion years. I don't expect that they're going to degrade and go away anytime soon. So what column am I going to pull from? Well, it looks like I'm going to pull from my stable column, right? So how am I going to make a proton? Well, I know that I have to arrange, right, 3 quarks to get a charge of plus 1e. All right, so what's the charge on an up quark? All right, 2/3 e. All right, so I have 1 up quark. There it is. Let's put 2/3 e there. What else am I going to add? Well, let's take another up quark. 2/3 e plus 2/3 e, right? And so there's another up. But what do I have to get here? I got to get this to be equal to 1. So 2/3 plus 2/3 is 4/3. It looks like I'm going to have to get what? A down, because that's minus 1/3, right? So if I subtract 1/3 e, 2/3 and 2/3 is 4/3 minus 1/3. Lo and behold, I get 3/3, which is 1e. By the way, did I satisfy my 2 rules? Integer number? Yes. Do I have any quarks and anti-quark pairs? Like, would I have a U and is there a U and an anti-U? No. A D and anti-D? No. So guess what? I've satisfied that as well. So guess what I have? I have a viable particle. Okay? So, sounds strange, but guess what? Every proton in your body, every single one, right, consists of 2 ups and a down. Let's take a look at another particle that should be familiar to you. Right? Let's get a neutron. What's the charge on a neutron? Well, hopefully you know that it's 0e. Right? So I have, right? And I'm going to tell you, a neutron is also a baryon. Right? So somehow I got to arrange, right, 3 quarks from our stable column to give me 0e. So let's say I'm going to put a U there. So there's a U, 2/3 e. What do I have to do? I got to get rid of, right, the 2/3. So if I put a down and a down, minus 1/3 e minus 1/3 e gives me what? Lo and behold, 0e. Right? So guess what? Did I break any of my rules? I did not. We are good. So guess what? Every, right, neutron in your body is consisted of an up and 2 downs. Now, just to let you know, there are many other strange particles that can exist. Notice what I'm saying here. I'm saying can exist. I'm not necessarily saying does exist. We produce these things in particles, accelerators all the time. They're around for a little while, and what do? They disintegrate. Is that okay? So this is what we believe, right? The universe is made from, okay? So this is our last little video that I'm going to ask you to do. I'm going to put a couple of things on Test Wizard, right? And that'll be it. All right, guys. Talk to you soon.